Okay, so after our lengthy calculation of this formula that gives you the length of a curve given in spherical coordinates, a curve that lies on a sphere, let me say two more things about this calculation and generally geodesics on a sphere. First of all, we had last time placed our point P as the North Pole and our point Q on the sphere so that it actually lied on the xz plane. What that meant was that the spherical coordinates of point P were both 0, while the spherical coordinates of the point Q were 0 on the theta and phi 0 on the phi coordinate. And if I take the arc of the great circle between P and Q, then every point on that arc, of course, also lies on the xz plane. If P lies there and Q lies there, then the entire arc is going to lie on the xz plane, which means for every one of those points, the theta coordinate is 0. In particular, the theta coordinate is constant, which means this part here is 0 for points on the arc of the great circle. Connecting P 0, 0, 1 and Q, which was x 0, 0, z 0. Okay, because that entire arc lies on the xz plane. So that means theta is constant, it's always 0, so that derivative is 0. So in that case, this integral, so L of c, where now c is the arc, let's actually call this the arc A. Okay, so in this case the length of A is just equal to this. And you actually recover the formula that we found by elementary methods. You get that the length is equal to phi 0. Okay, but I wanted to now briefly mention what happens when we move that point Q0 and actually place it on the opposite pole. In this case, of course, if I take a great circle that goes through P and Q, then there is no shorter arc. Both of the arcs have the same length, and the length is pi. However, not only that, there's not only one great circle that goes through them. If the points are antipodal, then infinitely many great circles go through these points. Right? There is, I'm just going to maybe draw two. So here's one great circle, but you can also have another one, say here, or on the other side. All of these are great circles, so there are actually infinitely many geodesics between P and Q. But note, while the geodesic is not unique between these 2 points, they all have the same length, so you can still define the distance between the antipodal points also, to be the length of any of the geodesics. If all the geodesics have the same length, then the length is the same, so you just define the distance to be that length. Okay, so the antipodal points on the sphere have distance pi. Yeah, so this is maybe my sort of last comment for this, is that we define the distance. The distance between any 2 points on S2 to be the length of the geodesic. connecting them. And this also makes sense, even if there's not a unique geodesic between 2 points. There's no unique geodesic only in one case, when the 2 points are antipodal. They don't have to be south pole and north pole. They could just be anywhere else, like on the equator, for example. As long as they're antipodal, there are infinitely many geodesics between them. But the distance, let's call it d, is well defined. And what actually is that distance? Well, as we said, that's the circumference of the arc of the great circle connecting them. So if I draw a sphere, and I pick any 2 points, I'm not even going to place them now on the North Pole. So here the center I'm going to mark in red, the center of the sphere. So I can then draw a ray from the center to the point P. And then I take another point somewhere else on the sphere, let's say here, Q. And there's a ray like that. And then I know there's a great circle that connects them, that connects these 2 points. So somewhere here is the arc of the great circle, right? The circle goes all the way around. That's the arc. So what's the circumference of this arc? Length. So the distance between P and Q. That's nothing else but the angle between these 2 points. Because again, the angle on a circle is the circumference of the angle divided by the radius. But if the radius is 1, then the angle is just equal to the circumference. So we get this formula. So the distance between P and Q is the angle between the lines. Let's call the center of the circle 0. It's the angle between these 2 lines, 0q and 0p, which can also be thought of as the angle between the 2 vectors. Vector from 0p and 0q.